Hello, everyone. Today we are going to be talking about the element distinctness problem. So first, what is the element distinctness problem? So the problem says that given an array of length n, we ask the question if all elements are distinct, right? So we input our array and then we output yes, all elements are distinct, or no, implying that there exist duplicates within the array. To solve this, we use comparison between elements in the array. So we're going to compare AI with AJ, and then this, is either going to result in AI is greater than, less than, or equal to AJ. We first sort all the elements, and then we compare adjacent points. And if any result of those comparison of adjacent point is equal, then we output no, right? Because that means they're duplicates. Otherwise, we're going to output yes. And we say that the time complexity for this algorithm, not for the algorithm, for the problem, is big omega of n log n time. So we can represent these comparisons by just a basic decision tree, right? So we have our decision tree, which is going to compare the ith and jth, elements in A, and that's going to give us one of three answers. Either it's less than, it's equal to, or it's greater than, right? And if it's equal to, that answer is no. And if it's less than, we compare the next set of adjacent elements, that gives us our own answers, all the way down until we compare the last set of adjacent elements, which will give us either yes, no, or yes, right? This is basically how the algorithm is working. It's like a visualization of what happens at each step of the algorithm, right? With each comparison, right? Again, this is all represented by a basic decision tree. So we want to analyze the lower bound. We want to see why the lower bound is actually big omega of n log n. So since we know the lower bound is big omega of n log n, we ask, how do we prove this? And an obvious answer is, or obvious initial strategy would be to use the sorting bound lower proof, right? Because they have the same lower bound time. And in fact, we use sorting within the algorithm. So let's take a look at that. So again, sorting says that we have an input array A, and our output is a sorted A with our running time, big omega of n log n. You can reference this lecture, Sorting Lower Bounds, which is at the end of the video, for a more rigorous proof of sorting lower bounds, but I'm not going to go into detail of the sorting lower bound proof. Basically, what happens at the end of the sorting lower bound proof, we see that there are at least n factorial leaves, right? Because there are n factorial possible answers, because there are n factorial possible permutations of the input array. And we are only looking for one specific permutation, which is the sorted array, A, right? So if we were to take a look or apply this method to the element distinctness problem, right? So the element distinctness problem only has two possible answers, right? So if we use sorting lower bound proof, which says that the height of the tree is greater than or equal to n factorial, pretty much, using that strategy on this sorting lower bound proof will tell us that the height is equal to 1, right? And that's not very logical, and we can see that from this, right? The height is obviously going to be greater than 1, right? So therefore, the sorting lower bound proof is not going to work. So we need a new method to show us that there will be at least n factorial leaves that are all giving a distinct yes answer, right? So before we jump into the proof, it'd help to go over a little background first. So what we're going to do, it's going to help us to interpret the array as an n-dimensional vector in real space, and we restrict that array, the entries in the array, to be the unit nq, right? So every element in the array is going to be bounded between 0 and 1, inclusive. We also want to define what a connected region is. So the definition of connected region is that for any 2 points in our region R, there exists a path that passes entirely through R. And then for a convex region, it's very similar to connected region, except instead of being any path, we restrict it to the straight line path from X to Y that passes entirely through R, right? So convexity is a much stronger statement to make, right? Because we're restricting how that path can look. And we can say that convexity implies connectivity, right? Just because convexity is a more stronger argument than connectivity. So we can take a look at an example of what convexity and connectivity are. So first, let's look at convexity. So say we have like this kidney-shaped bean thing, like a red bean. And we have 2 points here and a point there, right? So we can easily draw a path that may look something like that. And so since that passes through the entire region R, we say that this is in fact connected. But again, if we were to draw a straight line like that, that can't happen due to the definition of a connected region, right? Because it has to pass entirely through R. This point does not pass entirely through R. So we can easily say that that point is not, that's not a valid path for a connected region. So for a convex region, so say we have, this basic square. So it should be fairly obvious that any 2 points on this square must be connected by a straight line. So those are just 2 arbitrary points, and it's very clear that they are connected by a straight line and that it passes entirely through this region R. So then we can say that this is convex. So since this line is a path P and it entirely is passing through the region R, then it's very clear to see that convexity is in fact implying connectivity, right? So again, this is a convex region because we can have a straight line path from here to here, from this point to this point. This is connected but not convex because if we were to draw a straight line path, right, well, that would break, that would not pass through the entire region R. So therefore it is connected, but it is not convex, right? Okay. It'll make sense why we interpret the array as an n-dimensional vector when we get to the proof of, when we get to actually proving the claims. So bear with me for a second. So our proof is going to consist of 3 claims. Our first claim is let the region of L be the instances for which leaf L is reached on execution of the algorithm. Then we say that the region of L is in fact connected. Our second claim is let X equal an n-dimensional vector that consists of distinct elements, and then Y is a non-trivial permutation of X. So then X and Y must reach distinct yes leaves. And then claim 3 says that the number of yes leaves is greater than n factorial, which implies that the running time is going to be big omega of n log n, right? So let's jump to the proof for claim 1 now. So again, claim 1, the region of L is the instance for which leaf L is reached on execution of the algorithm. Therefore, we say that the region of L is connected. So let's take a look at what exactly claim 1 means. So remember that we are interpreting our array as an n-dimensional vector, and then we are restricting it to the unit n cube, right? So if array is, if the length is 2, right? So then we have an x1 and an x2, and then, for the cube, this would be the length is equal to 3, right? So again, let's think about what this means. So when the algorithm first starts out, right, this cube is our entire region, right? And then as we pass through each node that meets a certain condition, either less than, equal to, or greater than, what we are doing is we're shrinking the region effectively. So if we think back to this decision tree, so say we have our leaf L over here, right? So at the beginning, right? We have access to the entire region in the beginning, right? So again, if we interpret it as 2 dimensions, we have access to the entire R. We have access to the entire R, which would be the unit square here at the beginning when before any conditions have been checked. So then as we follow a path down, what we're doing is we reach this this node, which is the greater than node, right? So what is that doing? Well, that's effectively shrinking our region, right? And so we can visualize this. So this red line is the instance where x1 is equal to x2, right? So this would imply that our answer is equal to no, right? But if we take this greater than route, right? So we're now looking at everywhere that x1 is in fact greater than x2, right? So that means we're looking at this entire region above the red line, right, if we're in 2 dimensions. Similarly, if we took the less than route, then we'd be looking at this entire region, you know, below the red line, because x1 is now less than x2, right? So every time we pass through one of these nodes, right, you know, we're shrinking our region. And so this similar argument can be made for 3 dimensions, right? So if we have x1 is equal to x3, instead of being just a straight path line, that's instead going to give us this entire plane. So if x1 is equal to x3, right, well then, which implies that the answer is no. But if x1 is less than x3, then we're looking at everything in front of this plane. So, you know, this goes upwards all the way up to up here. And if x1 was greater than x2, then, you know, we'd be looking behind the plane. So over here, over there, right? So again, every time we pass through a node, we're shrinking the region effectively. So at the beginning, we have x is in the region, and then as we pass through a node, so this is going to have its thing, so we come here, and then we ultimately reach here, right? So we start with instance x, which has access to the entire region R, whether that be in 2 dimensions, which is the square, 3 dimensions, which is the cube, and then we follow this green path all the way down to L. So on the execution of the algorithm, when we have x, which is going, and it reaches, it arrives at leaf L, right? So then we can therefore say that x belongs to the region of L, right? Okay, so that's basically what claim 1 is saying for the most part. So now let's actually prove it. So we let x is equal to the n-dimensional vector and let y equals another n-dimensional vector, and let them be 2 points that exist in the region of the leaf L. So on the execution of the algorithm, right, x is going to reach L by assumption, and similarly y is going to reach L by assumption, right, because they're 2 points in the region of L. So suppose we have a z where we define z as lambda xi plus 1 minus lambda yi, and for all I, that is for lambda is bounded between 0 and 1. So it's clear to see that if lambda is 0, then zi is equal to xi, and if lambda is 1, we have zi is equal to yi. So if lambda takes a value between 0 and 1, we can say that z is on the straight line path interior of x and y, right? And that's by the assumption of zi. Zi is given by the equation connecting the points x and y, right? So let's suppose that the root is equal to ij, and we suppose that the left branch is taking on the execution of the algorithm, right? So now we're looking at this branch being taken on the execution of the algorithm. So that would imply that, of course, xi is less than xj, and of course, yi is less than yj, right? Because that's what it means to take the less than branch. If we plug this into z now, right? So we're taking xi and yj, we're taking like a linear combination of them almost. Well, of course, that linear combination of xi and yi is going to be less than a linear combination of xj and yj, right? And that's because xi is less than xj and yi is less than yj. So from that, we can say that the less than branch has to be taken where the instance is equal to z. And then this is a similar argument for any other branch taken when doing the comparisons. So then we say that RL is convex because there's a straight line connecting the 2 points. Thus, RL is connected, right? And so now we have proven claim 1. So now we can move on to claim 2. So claim 2, what does claim 2 say? We have x is an n-dimensional vector of distinct elements, and y is some non-trivial permutation of x. Then x and y must reach distinct yes-leaves. So before we jump straight into the proof of claim 2, it's going to be useful to us to prove this lemma, which says that there exists an ij such that xi is less than xj, while yi is greater than yj. So it's going to help to have an actual visual example when doing this proof, just to refer back to. So here we have x, right, which is just some vector of distinct elements, as you can see. Y, which is equal to sigma x, which is just a non-trivial permutation of x. So then we have pi of x, which is the sorted permutation of x. And then we have pi of y, which is the same permutation that was applied to x, but now being applied to y. So whatever indices were arranged when sorting x, we use those same indices rearrangements when making this permutation of y, pi y. So from here, it's clear to see that if I is less than j, then pi xi must be less than pi xj, right? Of course, because pi x is sorted, right? So that makes sense. So we can see that y cannot be increasing due to the formation of pi of y, right? So since we grabbed the indices, or we rearranged the indices x of x to give us a sorted permutation, but if we apply that same thing to y, right? Y can't be increasing because we specifically applied the increasing to x, right? So the indices that were grabbed, right? It just can't be increasing just because of how we took the rearrangement. So because y cannot be increasing, there exists an I and j such that I is less than j, and pi of yi is greater than pi of yj. So if we look at the second and fourth column for pi x and pi y, right, this is pretty easy to see. So where I equals 5 and j, if I equals 0.5 and j equals 0.8, right, we can see that in pi of x, 0.5 is, or if I equals 2 and j equals 4, 0.5 is less than 0.8, right? But if we look at y, we see that 0.8 is actually, in fact, greater than 0.7, right? So now we want to kind of retrace this, so we proved this for pi y, but now we want to retrace this back to y itself. So we can map those I and j's back to x and y, right? So, and then after that mapping, it's clear to see that xi remains less than xj and yi remains greater than yj, right? So again, map that 0.5 and 0.8 and pi of x back to x, and map that 0.8 and 0.7 back to y. We see that this last statement holds where xi is less than xj and yi is greater than yj. Thus, we have proved that there exists the ij where xi is less than xj and yi is greater than yj. So with that, we can jump straight into the proof of claim 2 now. So if x consists of distinct values, that means that the answer of x is going to be yes, right? And so if y is just a permutation of x, that means the answer of y itself is also going to be yes. So now we suppose that x and y are going to reach the same leaf L. So we know that RL is connected by claim 1, right? We proved that. So if it's connected, that means there's going to be a path from x to y that is passing entirely through L. Right, and so now by the lemma that we just proved, we can say that there exists an ij, so xi is less than xj, while yi is greater than yj. And now let's define a function f of w such that f of w is equal to wi minus wj, right? So If we apply this function to x and y respectively, this is going to give us that f of x is less than 0 and f of y is greater than 0. So then if we make a path between x and y, that's going to have to cross 0. So then by the intermediate value theorem, we can say that there exists a z in P such that f of z is equal to 0, right? So well, what does it mean for f of z to equal 0? Well, that means that zi is equal to zj, which implies that the answer of z is in fact no. Well, this is a contradiction because we assumed x and y must reach leaf L, which says that z must reach L, right? And that's by the previous claim that we just proved. So we have this contradiction, so therefore we can say that x and y must reach distinct yes leaves. And now for the last part, which is claim 3, so now we need to prove that the number of yes leaves is greater than or equal to n factorial, which is going to give us our lower bound omega n log n. Right, so from claim 2, we saw that each unique instance of x, right, so each unique permutation of x is going to have to reach a distinct yes leaf, right? So therefore, the number of leaves must be at least n factorial, right? And so then from this, using techniques similar to what was done in sorting lower bound proof, we can easily get that the running time is in fact big omega of n log n. So in summary, what have we done? We defined a region and what it means to be connected, right? We proved that the region of L is connected, right? We showed how x and y, being a permutation of x, must reach distinct yes leaves, right? And then we show how each, from that, we showed how each unique instance is going to have to reach a distinct yes leaf, which gives us our concluded lower bound running time of big omega of n log n, right? So these are some references. So this first video is a phenomenal explanation on the element distinctness problem. If I went over this too fast by any chance, or there were some parts that you're iffy on, this YouTube video goes much slower through the proof. And he does an excellent job of explaining the proof in general. And then if you wanted to look into the sorting lower bound proof, this lecture from, I'm not sure which university it's from, but this lecture gives a great explanation of what the lower bound proof is, showing the height of the tree, how we have n factorial different leaves. So with that, I hope you learned something from this video. I hope you're able to take away why the element distinctness lower bound is in fact big omega of n log n. And I appreciate you watching and listening. Thank you.